the last set of reactions that we have are the SN1 and the E1 reactions. Now, let's consider this reaction right here. Tert butyl bromide with ethanol. That ethanol not only is our nucleophile, our base, but it's also our solvent. So for SN2 and E2 reactions that are concerted, we would want a polar aprotic solvent. Now that we have a polar protic solvent, these actually stabilize the cation that could form a positive charge because of the ability of the oxygen to have ion dipole forces. And so what we see in this reaction is not only a mix of substitution and elimination products, but what we will also see is that the only way to get that tertiary center to undergo a substitution is if it is not via an SN2 concerted reaction, right? Ethanol is not strong enough as a base. So SN2 is not possible. E2 is also very unlikely because of the strength of ethanol. So what it turns out is that this reaction instead follows first order kinetics. The rate of both of these reactions, the substitution and the elimination, will only be dependent on the electrophile. We don't care about the base or the nucleophile. They're not part of the rate determining step. So it's important to be able to walk through these mechanisms to see the similarities and the differences. The mechanism of substitution and elimination in this case start with the same step, the ionization of the substrate or the starting material, which in this case is the loss of the leaving group. Bromine is going to leave so that we can form ions. Bromine, remember, is a halogen. It has 3 lone pairs. By leaving, it becomes that stable conjugate base that we talked about. It's a good leaving group, but why this reaction can be seen as a first order reaction, loss of leaving group by itself, is because we have a carbocation as well. So remind us of our carbocation stabilities. Allylic is the most stable carbocation, then tertiary, then secondary. Primary and methyl carbocations rarely form. What we are going to see is that SN1 and E1 are really good for tertiaries and allylics, but also secondaries can undergo them kind of, sort of, not very well. They're really slow, but rearrangements can occur to help stabilize those secondary carbocations. Now from here, after that first step, that rate determining step of loss of leaving group, this first step can actually funnel us in to both the substitution and the elimination. Again, for abbreviation purposes, SN1, nucleophilic substitution unimolecular. Only one molecule is dependent for that rate determining step. E1, elimination unimolecular. After that carbocation is formed, it will either undergo a substitution or an elimination depending on how it reacts with the solvent. The substitution reaction, so we're going to write it over again. The substitution reaction will look like this. Two-step process starts with the loss of leaving group. So bromine picks up its electrons and runs. We get a carbocation. I'm going to write Br minus down at the bottom so that it's not clouding my view of the next steps. We want to think about the nucleophilic attack coming in next. Ethanol is going to come in for our second step of nuke attack. Remember, the more reactive nucleophile will attack that carbocation. Br minus is not the more reactive nucleophile. Think about the stability of both of these as bases. Br minus comes from HBr, which has a pKa of -9. If you think about a protonated alcohol, that's about -1.7. So ethanol is a more reactive base than Br minus. It's kind of a weird thing to think about since we usually attribute that minus charge with reactivity. In this case, look to the pKa's and look to understanding those differences. Even ARIO, Br minus is much more suited to hold a negative charge than oxygen. And in this case, oxygen here, even though it's not negatively charged, is a much stronger base. What we end up with is we have to do a little bit of a cleanup step at the end. So thinking about that nuke attack, the last thing that we want to be able to do is clean up that oxygen with the formal charge of +1. We'll use another equivalent of solvent to do a final proton transfer, step number 3. Why we need to do this is so that our final product, our ether, is not protonated. This is our final substitution product. The entire mechanism is 3 steps. That last step is just a proton transfer to make sure that we clean up our final product. This is also called solvolysis because the solvent is acting as the nucleophile here. The highest energy intermediate, notice that we have 2 intermediates here, intermediate 1 and intermediate 2 with our reactant and our product. We'll construct the reaction coordinate diagram in class together, but it is a 3-step reaction total, the last step just being a proton transfer. The overall loss of leaving group and nuke attack is what the textbook does focus on as the main 2 steps of this reaction. The first intermediate is higher in energy than the second intermediate. Carbocations are very unstable. They're carbons with a lack of an octet. That's the reason why they have the +1 charge. Notice the oxygen there has a formal charge of +1, but it doesn't have a lack of an octet. It's just having an extra bond. All right. The E1 mechanism, the reaction of this tertiary substrate, starting material, again, starts with the loss of leaving group. Step number 1. That is the step that is most important to look at. Will this reaction happen? It's the rate determining step. Did I make a carbocation that is stabilized? That makes sense. And then what we want to establish for our E1 reaction is we have alpha and we have a variety of betas. All 3 of those carbons that are beta are identical. They're all identical. They're all methyls. So I'm just going to pull off 1. Excellent. And then ethanol will come and do the second step of our proton transfer. We roll that pi bond down in between alpha and beta. There's alpha, there's beta. We also do make a protonated ethanol, and we also have Br minus floating around in solution. So just some general ideas here. The rate of the E1 is the rate law is the same for E1 and SN1. In both cases, that first step is the rate determining step, the slow step, right? And so when we think about ethanol here, it's serving as a base as well as the solvent, right? So same kinetics when we think about what affects the rate of the reaction. It's the electrophile, right? It's not going to be the base or the nucleophile That is unimportant. It's in a subsequent step and it's not going to be the slow step. So really what we want to be able to think about with the SN1 is we really just see tertiaries and allylic carbocations. Sometimes secondary carbocations can undergo this reaction. For the E1, the same thing, we still need to make a stable carbocation. And so we can just think about copy, paste. Lovely, right? Really important to get that idea of what is required of that electrophile since it is the rate determiner. So again, here's the reaction coordinate diagram, at least for the first two steps of each E1 and E2. It's nice to compare these two. Both share that first step, reactants through transition state 1 to our first set of intermediates here. Then they diverge after that to a second transition state. And so it's important to be able to identify what type of a reaction are you doing. Now, rearrangements can occur, right? So when we look at this reaction, I would look first and say, okay, there is a secondary alkyl halide. Cool. Let's look in water. This is a weak nuke, and it can also be thought about as a weak base. So right now I'm focused on the E1 and the SN1. Both of these reactions will happen. But notice after step number 1 of my proton transfer or my loss of leaving group, I have a secondary carbocation, and adjacent to it, right next door on what would be my beta, there's a more substituted center. So all those carbocation rearrangements that we had before, 1,2 methyl shifts, 1,2 hydride shifts, they can occur here. They will. Remember, intramolecular reactions are way faster than intermolecular. So that water is not going to come and react until that carbocation has already shifted secondary to a tertiary. Definitely more stable. Then we can keep going. Let's look at water just as our SN1 reagent first. There you go. Do our nucleophilic attack. We will need to do a proton transfer on this as well for our last little cleanup step. Water can pull off that proton to make our final substitution product, the alcohol. But notice how what we originally called our alpha carbon is now changed, right? The actual carbon that got the substituted product is now different. All right, same thing. I can take this guy, and I'm just going to give myself some room and use water for the E1 reaction. And if this is alpha, I have some options for beta. Beta 1, same as over here, beta 1. There's an H there though too. Don't forget beta 2. I'm just going to erase one of the beta 1s because they're the exact same. I'll deal with beta 2 first. What's good to note, again, while we're getting used to this mechanism, is there any stereochemistry, cis or trans? There is still a stereoselectivity with this reaction. We like trans versus cis, but there's no anti-periplanar with the E1. There's no backside attack with the SN1. So we make all sorts of racemic mixtures and all sorts of chiral centers. I'm going to just present here alpha, and I'll hang off beta 1. Draw another water. I'll put it right up there though for my E1 with my other beta. That plus charge. Again, neither of these have stereochemistry because each one has at least one side where there are identical groups. So there's no prioritizing with these two. But in terms of stereoselectivity and regioselectivity, if we did have cis and trans, we would definitely favor the trans over the cis. Here, with all three of these products, 1, 2, and 3, we will definitely favor our elimination product that is more substituted. Water is very, very small, so we can think about those E1 reactions always giving the most stable alkene possible. All right, so we can think about solvent, and our last idea here is understanding our polar protic solvents. So notice this is a tertiary alkyl halide. It's going to form a carbocation in that first step, loss of leaving group, the rate determining step of our SN1 and E1 reactions. Notice the difference between polar protic solvents and that relative rate of reaction. So how much, you can think about this as product amounts, right? They're normalized so that you can see the difference. Water is very good at stabilizing carbocations because of the two areas of hydrogens of delta pluses and oxygen being very available with its delta minus to stabilize positive charged things. And as you get down to the polar aprotics, notice these values right here, they're very, very low. Polar aprotic solvents with our SN1 and E1 slow the reaction rate down drastically. So make sure that we are identifying when we form a carbocation, we want polar protic solvents, things with a polar proton. And when we have our non-carbocation reactions, our concerted reactions, SN1 or SN2 and E2, we want our aprotic solvents, the ones that don't really care about stabilizing carbocations. Again, the regioselectivity here, just to sum up and to finalize, just like with E2 reactions, it is possible for E1 eliminations to result in more than one regioisomer, regioselectivity, Hoffman versus Zaitsev. E1 will always give the more substituted alkene, just always. We cannot control the regioselectivity like we did with big or small bases. E1, because of the carbocation, there's a limited amount of steric hindrance at any rate, so we will always get the more substituted product. No Zaitsev or Hoffman control. It is further possible to obtain several different alkenes, right? So many things open up with our E1 reactions. And so again, we'll get all different products, but the E isomer is always more favored than the Z isomer.